Welcome to the Curious Machine. We often hear this idea that feels totally solid, right? That nothing comes from nothing and nothing just disappears. It feels like common sense. And we apply it all the time to energy. Energy is always conserved. But here's a thought. If the universe definitely had a beginning, which, well, science tells us it did, does that maybe poke a hole in this idea? Could energy conservation, the idea that energy is sort of eternal, actually be?
Mhm.
Well, maybe not the whole story.
That is exactly the fascinating question we're diving into. We're going to unpack what energy really is.
Yeah.
It's maybe not what you think. Then we'll trace how we even came up with this conservation idea. It's quite a journey. And finally, we'll look at where this bedrock law might, surprisingly, not quite apply.
Okay, let's start there. What is energy? We talk about it constantly, but defining it feels slippery. It's almost easier to point at things like that person has a lot of energy or that car is using energy. We feel it, we see its effects.
You've hit it right on the head. It's a challenge. In physics, the sort of textbook definition is the ability to do work. And work, in physics terms, just means the energy transfer when a force makes something move. But here's the kicker, the really interesting part. Energy isn't some fundamental thing in the universe like space, maybe. It's more like a concept we invented.
A concept, like an accounting system.
Exactly like that. Think about money. The paper itself isn't valuable, right? Its value comes from everyone agreeing it represents purchasing power. Energy is similar. It's a really useful way we've come up with to track transformations happening in the universe.
So it's a bookkeeping tool for the universe's changes.
Precisely. We see things happen, and we describe those happenings as energy changing from one form to another.
And that's conservation of energy. It doesn't pop into existence or vanish. It just shifts around or changes its costume.
That's the core idea.
Yeah.
And we have tons of names for it. Kinetic, potential, formal, chemical, nuclear, light, sound. So many. But fundamentally, you can boil almost all of them down to just two basic types. You've got kinetic energy, which is the energy of motion, things moving. And you've got potential energy, which is basically stored energy, energy that could cause motion later.
Okay, simplify that, like nuclear energy.
That's a form of potential energy stored in the nucleus of an atom.
Mhm.
And heat, or thermal energy,
Yeah.
that's really just the average kinetic energy, the jiggling of tiny atoms and molecules.
So it all comes back to motion or the potential for motion?
Pretty much, yeah. It's all about movement, seen or unseen.
Okay, let's use that classic example. An apple falling from a tree branch. We say it starts with potential energy because of its height, right? Then as it falls, that turns into kinetic energy, the energy of motion.
All right.
But then splat, it hits the ground, it stops. Where did the kinetic energy go? Did it just disappear?
Good question. It looks like it disappears from our everyday view. But no, it's conserved. When the apple hits the ground, that big picture kinetic energy gets converted, mostly into heat. Think about the sound it makes, the slight warming of the apple and the ground where it hit, even the air it pushed through. Microscopically, that heat is still kinetic energy. It's the molecules in the apple and the ground vibrating faster.
So it's still there, just spread out and harder to see.
Exactly. But this brings up something really important. The idea of a control volume. The amount of energy you measure totally depends on what you decide to include in your measurement, your system's boundaries.
How so?
Well, that apple looks stationary on the ground relative to you, right?
Yeah.
But if you were watching from the moon or even another star system, that apple is whipping through space because the Earth is spinning and orbiting the sun. From that bigger perspective, it has enormous kinetic energy. So energy isn't some absolute number. It depends on your frame of reference, your control volume.
Wow, okay. So energy is relative. Its conservation depends on where you draw the lines. Mm, this is getting complicated. Which makes me wonder, how did we even land on this idea of conservation? If it's not absolute, what's the real story? Sounds like we need a history lesson.
It was definitely a long and winding road. You had ancient philosophers, sure, with vague ideas about some underlying stuff that doesn't disappear, Thales, Epicurus, but not really energy as we know it. The scientific gears started turning much later, maybe around the 1600s. You had Simon Stevin, who figured out perpetual motion machines were impossible. That hints that something can't be created from nothing. Then Galileo, studying pendulums and things, he noticed how potential energy changes to kinetic and backward, how something swings back up to roughly the same height it started from. Inertia was part of that picture.
Right, and Christian Huygens studied collisions, finding things that were conserved, like momentum.
Yes, though the picture was still fuzzy, especially distinguishing between bouncy and sticky collisions. but momentum was a key piece.
And then came the big debate, wasn't it? Newton versus Leibniz.
Oh yeah, a huge one. Newton championed momentum, mass times velocity, as the truly conserved quantity. But Leibniz proposed something else he called visiva, which means living force. It was mass times velocity squared.
Which is basically kinetic energy.
Exactly. He had stumbled onto kinetic energy,
Hmm.
but it led to this really intense, almost bitter debate, tangled up with their different philosophies too.
So who settled it? How did they figure out Leibniz was onto something crucial?
The hero of this part of the story, and sadly often overlooked, is Émilie du Châtelet, a brilliant French mathematician and philosopher in the early 1700s.
What did she do?
Building on some earlier experiments, she did this very clever thing. She dropped metal balls from different heights into soft clay, and she carefully measured how deep the dents were. What she found was that the depth wasn't just proportional to the ball's speed, its velocity. It was proportional to the mass times the velocity squared, just like Leibniz's vis viva.
Ah, so the impact, the work done on the clay, depended on kinetic energy.
Precisely. It was elegant proof. And she didn't stop there. She also did foundational work on the formula for potential energy mass times gravity times height. Really crucial contributions.
Okay, so vis viva, or kinetic energy, was established. But what about heat? When things rub together, they get hot. Where did that fit in?
That was the next big puzzle. Scientists started suspecting that the heat from friction wasn't lost energy, but maybe another form of this vis viva.
Makes sense. You rub your hands together, that's motion, and they get warm.
Right. People like Lavoisier and Laplace reviewed ideas about heat. Then Count Rumford made these famous observations while boring cannons. He noticed an incredible amount of heat was generated, seemingly just from the mechanical motion of the boring tool. Its strongest suggested motion could turn directly into heat quantitatively.
So heat wasn't some weird fluid, it was related to motion.
Exactly. And around 1807, Thomas Young actually first used the word energy in the way we use it scientifically today. Then others, like Coriolis and Poncelet, refined vis viva into the precise concept of mechanical work. And by 1837, Carl Friedrich Mohr made one of the first really broad statements connecting motion, chemical reactions, light, magnetism, suggesting they were all forms of one conserved thing.
This is all leading up to figuring out exactly how much work equals how much heat, right? The mechanical equivalent of heat.
Yes, that was a linchpin. Lomonosov had suggested heat was motion much earlier. Then Julius Robert von Mayer, a German doctor, noticed patients in hotter climates needed less oxygen connecting metabolism, which is chemical energy, to heat production. He figured out the equivalence principle independently. But the really definitive experiments were done by James Prescott Joule around 1843.
The Joule apparatus, I remember that from school. Weights falling and turning paddles in water.
That's the one. He meticulously measured the falling weight, which lost potential energy, and the tiny temperature rise in the water, which gained internal energy or heat. He showed a precise quantitative link. A specific amount of mechanical work always produced the same amount of heat.
That really nailed it down.
It did. And then scientists like Grove and Helmholtz tied even more things together. Electricity, magnetism, light, showing they were all interconvertible forms of this single thing called energy. By 1850, William Rankine officially coined the phrase we still use, the law of the conservation of energy.
What a journey. From vague ideas to precise experiments. But then, the 20th century arrived and Einstein turned things upside down again.
He certainly did. Before Einstein's 1905 theory of special relativity, everyone thought mass conservation and energy conservation were two separate laws. You couldn't destroy mass, and you couldn't destroy energy.
But Ehm and sequence changed that.
Fundamentally, it revealed that mass is a form of energy, an incredibly concentrated form, what we call rest energy. So mass can be converted into other energy forms like kinetic energy or light, and energy can be converted back into mass.
So the two laws merged into one.
Exactly, the conservation of total mass energy. You see this in nuclear reactions where a tiny bit of mass vanishes and releases huge energy. That's the mass defect. Or even more dramatically, when matter meets antimatter, like an electron and a positron annihilating. Their entire mass converts purely into energy, into photons.
Okay, so we have this incredibly well-established law, refined over centuries, uniting mass and energy. But why? Why is total mass energy conserved? What's the ultimate reason?
Now we get to the really deep, beautiful insight. And it comes from another giant of physics, contemporary with Einstein, but someone who faced enormous barriers. Emmy Noether.
Emmy Noether, a mathematician, right. I've heard her name, but she doesn't always get the spotlight Einstein does.
Tragically so. She was a German mathematician of profound genius, worked for years unpaid because of her gender. Her work fundamentally changed physics. In 1918, she published what we now call Noether's theorem, and it's mind-blowing. It says that conservation laws, all conservation laws, including energy conservation, aren't fundamental rules on their own. Instead, they are direct mathematical consequences of underlying symmetries in the laws of nature.
Symmetries. What does that mean in physics terms, like a shape being symmetrical?
Sort of, but more abstract. It means the laws of physics themselves don't change when you change something about the situation, like where you are, or when you are, or what direction you're facing. Think about dropping a ball. The law of gravity works the same way today as it did yesterday, right?
Yeah.
And it works the same in London as it does in New York, or presumably on Mars. The laws are the same regardless of time or place. That sameness, that invariance, that's a symmetry.
Okay, so how does symmetry lead to conservation?
Noether proved a direct connection. If the laws of physics are the same over time, if they don't change from moment to moment, which we call time translation symmetry, then energy is necessarily conserved.
Wow. So energy conservation isn't a rule, it's a result of the fact that physics doesn't randomly change day to day.
Exactly. And there's more. If the laws are the same everywhere in spatial translation symmetry, then linear momentum is conserved.
Okay.
And if the laws are the same, no matter how you rotate your experiment rotational symmetry, then angular momentum is conserved.
Hmm.
Even for a lumpy, non-symmetrical asteroid skidding in space, the laws governing its spin are rotationally symmetric, so its angular momentum stays constant.
That's incredibly elegant. It ties all these conservation laws together under one principle. Symmetry.
It's profoundly powerful. It gave physicists a completely new way to understand where these fundamental laws come from. It's become central to everything, especially in quantum mechanics, understanding things like charge conservation through what are called gauge symmetries.
So the conservation of energy emerges from the fact that the fundamental rules of the universe don't change over time. That feels very solid.
It is incredibly solid, locally. But now comes the big cosmological twist you hinted at earlier,
The caveat.
the caveat. Noah's theorem, in its standard form, kind of assumes that the background, space-time itself, is fixed and unchanging, flat in geometric terms.
But Einstein's other theory, general relativity, tells us space-time isn't fixed, right? It's dynamic, it can warp and curve and expand.
Precisely. Our universe is expanding.
Yeah.
And on the vast scale of the entire cosmos, space-time is not static, it's stretching. This means that the condition for Noether's theorem regarding energy, that perfect time translation symmetry across the whole universe, doesn't actually hold on that grandest scale.
Oh, wait, if the symmetry breaks down because the universe is expanding, does energy conservation break down too? On the scale of the whole universe.
The evidence strongly points to yes. Energy is not strictly conserved on a cosmological scale.
Whoa. How do we know?
The most striking example is photon redshift. Think about light from a galaxy billions of light years away.
Yeah.
As that light travels towards us, the universe itself is expanding. Space is stretching, and the light waves get stretched along with it.
Great, their wavelength gets longer, redder.
Exactly. But a photon's energy is directly tied to its wavelength. Shorter wavelength means higher energy. Longer wavelength means lower energy. So as these ancient photons travel through expanding space and get redshifted, their energy literally decreases. It just fades away. It doesn't transfer anywhere else. It's lost because of the expansion of space-time itself.
The energy just vanishes. Poof.
In that cosmological context, yes, it diminishes. Another huge puzzle is dark energy.
The mysterious stuff accelerating the expansion.
That's the one. Now, as the universe expands, normal matter and radiation get diluted, the same amount spread over more volume, so their density drops.
Makes sense.
But dark energy seems to have a constant density. As the universe gets bigger, the density of dark energy stays the same, which means as the volume increases, the total amount of dark energy in the universe must be increasing. More energy is appearing out of nowhere, seemingly, to keep the density constant in an ever larger space.
That sounds like a massive violation of energy conservation.
It certainly appears to be. On a simple reading, it's a profound mystery.
So what do physicists do with this? Just throw out energy conservation for cosmology? Or are there attempts to, save it?
It's a really active area of thinking and debate. Some physicists argue that energy conservation just isn't a well-defined concept on the scale of the entire expanding universe, precisely because that background time symmetry is broken. You can't apply Noether's theorem globally. Others try to find ways around it. Maybe there's some kind of gravitational potential energy of the entire universe that balances things out so the total net energy remains zero. Alan Guth famously called this idea the ultimate free lunch, the universe starting from basically zero net energy. But these are tricky speculative ideas.
Is there anything similar happening in quantum mechanics? Any fuzziness around energy conservation there?
Well, on average, energy conservation holds incredibly well in quantum systems. It's fundamental to the equations. However, there are some interpretations and theoretical ideas, especially related to measurement, that explore whether energy might not be perfectly conserved in individual quantum events, just on average over many. It's debated, and there's no solid experimental proof of violations yet. But, and this is really important for perspective, for absolutely everything we do here on Earth, in the lab, in the solar system, energy conservation holds to astonishing precision. It's still one of the most reliable tools we have.
Right. So the cracks only appear when we look at the universe on its grandest scales, or perhaps deep within quantum uncertainty.
Exactly.
This has been quite the journey. We started with what feels like an absolute truth: energy is conserved, and found it's actually, well, more nuanced. It's a consequence of symmetry, incredibly reliable locally, but maybe not the final word cosmologically.
And that's the beauty of science, isn't it? Digging deeper reveals layers. Understanding why and when a law holds and where it might break down gives us a much richer picture of how the universe actually works. It's not about simple yes or no answers sometimes.
It definitely makes you think. And perhaps that leaves us with a final thought for you listening. In our everyday world, figuring out who's telling the whole truth can be really tough. But when it comes to the universe itself, if someone claims they have the complete, absolute, final explanation for everything, you can probably be sure they're missing part of the picture. The cosmos is still full of mysteries. The trick is knowing how to keep looking and what questions are worth asking next. Thank you for joining us on The Curious Machine. Until next time, keep exploring.
Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.